Hello, class. In this lesson, we will discuss the intermediate reflux in the atmospheric tower. In atmospheric tower operations, we often hear terms like first atmospheric intermediate and first vacuum intermediate. These refer precisely to the intermediate refluxes of the atmospheric and vacuum towers. So, what is intermediate reflux? In distillation tower operations, a stream of material is drawn from the middle section of the tower, cooled, and then returned to the tower as reflux. This is called intermediate reflux. Why is intermediate reflux necessary? What phenomena would occur without intermediate reflux? If we do not use intermediate reflux, then to maintain the overall heat balance of the tower, we must rely solely on top cooling for reflux. In this case, the cooling load at the top would be very large. Specifically, the air cooler load would be high. Cooling water consumption would be significant. And most critically, this substantial amount of heat cannot be utilized. It is simply removed by cooling, resulting in huge energy waste. Furthermore, because the top cooling capacity is limited, the tower's throughput is constrained under these conditions. In contrast, by employing intermediate reflux, the high temperature level heat can be recovered and utilized, thereby increasing the tower's throughput. In summary, the necessity of intermediate reflux lies in the need to maintain the temperature profile within the tower and fully utilize excess heat. Intermediate reflux is essential. Top reflux, also known as overhead circulating reflux, involves liquid drawn from several trays below the top of the tower. This liquid is cooled and then returned to the topmost tray of the tower. This ensures that all lower trays have internal reflux, thus meeting the requirement for liquid phase reflux in the tower. Besides recovering waste heat and equalizing the vapor load in the tower, the top reflux also bears the responsibility of ensuring the dry point of the crude gasoline meets specifications. In short, the role of intermediate reflux is to balance the vapor and liquid loads within the tower, while simultaneously extracting excess heat from the tower, thereby serving an energy-saving function. As shown in the diagram on the right, this process employs two intermediate refluxes. The draw temperature for the first atmospheric intermediate is 234 degrees Celsius, with a return temperature of 170 degrees Celsius. The draw temperature for the second atmospheric intermediate is 280 degrees Celsius, with a return temperature of 218 degrees Celsius. This approach both maintains the temperature gradient within the tower and achieves comprehensive utilization of heat. Next, let's discuss rational heat removal in the atmospheric tower. How can we achieve rational heat removal? This is the essence of atmospheric tower operation. Atmospheric towers are often equipped with both top circulating reflux and intermediate reflux. Top circulating reflux generally refers to the overhead product being cooled and then pumped back into the tower. It provides about 90% of the cooling duty at the top. Its primary function is to remove heat from the tower, maintaining its heat balance. It also provides liquid phase components to the trays, improving separation efficiency. The top circulating reflux stream remains in the liquid phase throughout the entire process, merely circulating inside and outside the tower. Heat exchangers are used to remove a portion of the residual heat. If the heat quantity is significant, recovering this heat can be considered reduced plant energy consumption. Without top circulating reflux, large condensers and coolers like air coolers and water coolers would be required. It could also lead to uneven distribution of vapor and liquid loads between the top and bottom of the tower, affecting reflux rates. Intermediate reflux is primarily used in complex towers, such as those in petroleum refining like the atmospheric tower. Its function is the same as that of top cold reflux. It rationally removes heat to maintain the tower's heat balance. Furthermore, regarding the cost and benefit of the atmospheric tower, for the same throughput, using intermediate reflux allows for a reduction in the tower's diameter and height. Similarly, for the same tower height and diameter, adding intermediate reflux can increase the throughput. Optimizing atmospheric tower operation mainly involves properly controlling the various intermediate refluxes and their return temperatures. Heat removal in the atmospheric tower is referred to as triangular heat removal. The temperature difference between the draw and return temperatures for the second atmospheric intermediate is close to 100 degrees Celsius. This is even greater than the temperature difference for the top circulating reflux. Thus, it carries out more heat. The purpose of heat removal is to establish internal reflux within the tower, facilitating thorough exchange of the cut components inside the tower. For atmospheric tower operation, to ensure vapor-liquid equilibrium operation within the tower, the heat removal by the intermediate refluxes should follow this order, from largest to smallest: second atmospheric intermediate, first atmospheric intermediate, top circulating reflux. This creates varying temperature differences between the trays within the tower. The internal reflux forms a temperature gradient from top to bottom. Generally, the temperature difference at the tower wall nozzles for the second atmospheric intermediate is around 100 degrees Celsius. For the first atmospheric intermediate, the temperature difference is about 70 to 80 degrees Celsius. For the top circulating reflux, the temperature difference is approximately 40 degrees Celsius. Alright, class, that concludes this lesson. See you in the next class.